going to talk to you about Orleans this morning, which is a new Microsoft technology which is available for you to use and play with. So I come from a company called 210 Degrees. We're based in this barn in Ipswich in Suffolk, and we're a kind of boutique software house. We're quite small, and we do a couple of things. So the first thing we do is we run a satellite communications platform as a service. So basically we put a REST API over the satellite network. So you can talk to any satellite-enabled device, like an Iridium phone or a device stuck on an oil pipeline somewhere in Russia, and you can get telemetry information back and you can send it messages and so on and so forth. So you can go and buy an Iridium phone and climb Everest and send a tweet from the top. But we also have devices on a large number of UK fishing vessels. So if a vessel turns over or a man falls off the vessel, the Coast Guard are alerted and the RNLI are sent out to pick the guy out of the water. And that's all running on the Azure platform with high availability, no downtime in the last few years. And out of our experiences in running this software in this way in Azure, we've kind of started an Azure consultancy business, which is where I work, helping companies around Europe understand what this cloud stuff is all about and what Azure is. And out of that and our relationship with Microsoft, we were kind of introduced to Orleans about a year before it came out and was made public. And that's given us a good chance to play with it and understand it. And we were involved quite closely with the release back earlier this year at Build. And we built a number of the samples that went with the release. And I wrote some of the documentation that came out with it as well. So we've got a good relationship with the product team out there in Seattle, and so we're really quite excited about Orleans and what it offers. So I'm going to tell you this morning about the basics of what it does, and kind of introduce it and pitch it, and then we're going to see some hands-on development if we're lucky. I'll leave plenty of time at the end for questions, so just raise your hand throughout the talk or at the end. So what's interesting, what we've observed over the last few years is that the hardware landscape is changing. And we're starting to want to build software that talks to lots and lots of devices out on the internet. When I first started programming and building websites, the number of people connecting to my service was fairly limited, fairly small. But we're starting to see many more devices out there, and many more people are enabled on the internet, and we're starting to see hundreds of thousands of things trying to connect to our services, and we're building gateways to handle this stuff. So we need some new ways of thinking about building software to handle this load. Hundreds of thousands of devices, we've got high message throughput. Some of these devices send very high rate telemetry through, and we often need to react very rapidly to what these devices are telling us. So for example, if a man falls off a fishing vessel in the North Sea, we need to know very quickly that that's happened. We can't have any latency. We're also seeing software platforms where we're not seeing the traditional vertical communication. So let's talk about a traditional web application. A request would come into your web server through your middle and data layers down to your database, and then the response will go back up again. But with Internet of Things type of systems and social networking and more modern architectures, we're seeing much more cross-server communication where servers are having to collaborate more in a distributed system rather than just being a lot of siloed applications. The hardware landscape is changing, and when I first started programming, I had a single computer with a single core, and I was writing my Turbo Pascal 6 and pretty happy. Didn't have to worry about threading or anything complicated. But we're now seeing many more machines with multiprocessors and lots of cores, and 8 is fairly standard now. In fact, the theoretical maximum on Windows Server is 320, which looks like this in Task Manager. So you can see each of those boxes represents a core on the machine, and most of them are completely idle. Apart from this one box here, which is maxing out at 100%. So there's one process on this system which is not making use of multiple threads. It's not able to split its work across multiple cores, and it's, as a result of that, being starved and could run faster if it could. It's probably Task Manager, but there you go. So it turns out that writing software for multiple cores is not straightforward. Concurrency is a hard problem. Why? because it's very easy to write code where you're getting two threads trying to compete for resource, trying to access the same variable at the same time, or set it, and you get all kinds of corruption. Object orientation, the tool that we've been trying to use the past few years, is letting us down, and people are seeking functional languages, or finding new languages, or digging up languages from the past, and they're becoming very popular because they solve a lot of these concurrency problems. Is anyone here doing kind of non-OO software because of this concurrency problem? Probably a lot of people in this room, which is why we're all attending this conference. It turns out that sharing mutable state doesn't work, and so a lot of these languages have non-mutating state as a principle. So this is some hard stuff, and of course, it's not the only way the hardware landscape is changing. We're starting to build our software to run in the cloud. So when I first started programming, I had this single machine, but now we can scale out to hundreds and thousands of machines. So we have to write software that we can deploy and run on all these servers. And of course, things like failure happens and a server will suddenly disappear, which is not something we ever expected to happen. Certainly when I first started programming in my Turbo Pascal, I'd be far more worried about hardware failure than I would about my crappy software. But now, hardware is disposable, and if a machine breaks in Amazon or Azure, it's fine, you just get another one. It doesn't matter, does it? You carry on. But we have to have software that copes with this failure and carries on and works well. So, programming for the cloud, it turns out building distributed systems is hard. Traditional architectures let us down. Failure happens. So these are all problems we need to deal with and think about. So let's talk about, going back to this Internet of Things, how we would build a Internet of Things gateway platform system that's going to receive all this information. With a traditional approach, we would have all of our devices connecting through to some front-end web server or something. It doesn't really matter what the protocol is, that's somewhat irrelevant. We're channeling them through some system to authenticate and authorize these devices. We then want to record the state of the device and persist the data somewhere. So a relational database is normally where people put all of their state and their concurrency problems. They shovel them all down into the data tier, and the database does the hard stuff of managing that concurrency. And we keep our web application nice and stateless, and that allows us to scale out horizontally without having to worry about concurrency. The problem with this approach is that after a while, we get a bit of latency because the database has to load stuff off the disk. But the bigger problem is that the database doesn't scale very well. And so it's very hard to cluster a SQL database. CAP theorem gets in the way. And so after a while, it falls apart. Now, there's ways of getting around this. You can shard your databases. You can have scale units, so you can have lots of systems all together side by side. And you funnel your traffic to the right place. But these are all kind of workarounds that buy you a bit more headroom, but don't really solve the problem. Other people have been looking to NoSQL. There's a couple of vendors here. And it's a very good solution. It allows us to scale much greater. But there's usually a trade-off with this approach. Not always, but usually we're trading off latency here. So we're putting a latency in our system. Perhaps we're using CQRS or some kind of eventual consistency model where we're introducing some delay in the write, which buys us the scale. But for my scenario, pulling people out of the water who are dying in the North Sea, it's not good enough to have any latency here. I want an immediate and consistent view of the world. So, sorry, those approaches don't work for me. I'm not saying that these approaches are wrong, but then for this scenario, building an Internet of Things, having a low latency and real-time view, these don't work. So, what can we do? Well, let's introduce Microsoft Orleans. It's codenamed Orleans at the moment. That's the project title. I expect one day they'll call it something else, like .NET Actor model for something or other. But for now, it's Orleans. What is it? Well, it's a framework for building distributed systems. Fantastic. It's been built by the Extreme Computing Group in Microsoft Research over in Seattle. So love them or hate them, Microsoft do employ some pretty smart people, and there's been a lot of time spent developing this. There's a research paper that's come out of it. There's some really good thinking, really good best practice built into this framework. Orleans has been designed from day one to run in the cloud, in particular Microsoft Azure. But in fact, it doesn't have to run in the cloud, and you can run it out of the cloud on premises or in different clouds, although I would actually recommend Azure as the best place to put it. And what is it in practical terms? Well, it's a .NET implementation of the actor model. Who's heard of the actor model here? I hope some people have. Robert has, I hope. It turns out the actor model is a really good idea, and we'll look into how Orleans implements the actor model. It's a slightly different approach to systems like Erlang. So Microsoft have been using Orleans internally for a while now, and their main user of the system so far has been this guy. Anyone recognize him? It's Master Chief from the Halo series. So the whole of the cloud services for Halo, the Halo 4 game, were all written in Orleans. So every time you do a headshot or you kill someone or some significant event happens in the game, the telemetry goes from the Xbox 360 up to the cloud, and that's all recorded in Orleans in one of the actors. Then when you use the second screen experience, or you go into the Halo portal and look at your game stats and your player statistics, that's all Orleans providing that information for you. So it's being used extensively, and it didn't fail on the day the game was launched, where they saw quite a huge volume of traffic there. So how would it look if we were to implement our IoT system using Orleans? We'd have a device, let's say we'll just look at one for now. It makes a request through to our web API. We still keep this kind of gateway. You wouldn't normally expose Orleans to the outside world. You'd always front it with your own system first. So you would then forward a request onto one of the servers running Orleans. And Orleans has something called a silo. A silo is just basically the service that's running the Orleans process, which reserves a large amount of RAM and is the host for the system. You'd normally host Orleans on at least 2 machines, possibly hundreds. When the request comes in, Orleans will create what's called a grain. Now, a grain is Microsoft speak for an actor. They called it a grain to try and differentiate themselves from other actor systems so they could talk about a unique nomenclature. I don't know whether that's confusing or helpful, but we'll from now on talk about grains in Orleans. So it kind of follows the farming semantic of silos and grains and so on. There you are. So a grain is activated. Now, at the point of you making the request, you don't know whether the grain is activated or not. Your web application that acts as the client to Orleans doesn't care. It's agnostic as to whether the actor exists. They call it a virtual actor model because the actors are created on demand. So the grain would process your request. It may well go and talk to another grain in another silo and can do cross-silo communication. And these things can collaborate and inform a response and inform the device if necessary. The grain then remains there after the request has been served and stays in memory for as long as Orleans deems it necessary. And it will keep it there so that when future requests arrive at the system, the grain doesn't need to be activated. It's already there waiting with its state in memory, ready to serve your response. In fact, the silos are designed to host hundreds and thousands of grains and keep them all in memory. So you can view Orleans as a bit like a cache. It's keeping the right things in memory at the right time to enable fast responses to requests coming into your system. Over time, though, Orleans will deem your grain as not required anymore and will mark it eligible for garbage collection. And in a garbage collection cycle, the grains will be removed from memory. You can be notified of this, and you can say, don't kill me yet, or you can ask to be killed straight away. So it's not like the Erlang model where you try and keep actors in memory and you have a whole management system which actors check other actors. That's not how Orleans works. It's, the silo manages the grain's life cycle, and the silo will go and terminate the grain to free up memory. It doesn't matter because the grain can then be reinstantiated when required, and any state that you had in the grain that you wanted to keep, you should have persisted while the grain was alive. So what does a grain look like from a programmer's perspective? Well, it's a small, simple programming model. A grain is supposed to be something small and easy to understand. The code inside the grain is always run in a single thread, so you never have 2 activations of your grain. You always have a single activation in the whole of the silo, and that single activation will only run 1 message at a time, and you can't do any kind of multi-threading in there. But you can do asynchronous stuff. Grains should always be asynchronous, non-blocking, and so they make good use of the threads available. So when I look at these 3 titles, small, simple, single threads and asynchronous, I immediately think of Node.js, which is probably why I quite like Orleans. It's easy to program. It's designed to make it convenient for a programmer, so you don't have to have a degree in distributed computing to be able to approach this stuff. A grain has internal mutable state, so it's okay to mutate state in Orleans, and you can have properties inside your grain that you maintain. If the state changes and you need to persist that, then you need to make a call to a persistence service to say, I need to save this stuff. But it could be volatile. Communication to and between grains is via asynchronous message passing, and of course, if the grain's already processing 1 message, then the message is queued on the mailbox for the grain to process in turn. The one thing that a grain can't do is have any shared state or modify the state of another grain directly. That's not allowed for concurrency reasons. So what is a silo? Well, a silo hosts grains, designed to host hundreds of thousands of grains, and it manages the life cycle of those grains, so it'll activate the right grains at the right time transparently to you. In physical terms, the silo is a .NET DLL or a console application. It's something you can host yourself and embed within your own code, or you can run it as a service. And silos are, of course, designed to work together in a clustered way, so they all talk to each other, and they maintain a membership system, so they know which other silos are available. It will also route messages to the right silo for where the grain is hosted. It knows where the grains are hosted in which silo. So how do we, so what are the advantages Orleans presents? Well, first of all, it solves all of our concurrency concerns we were talking about at the beginning, because you don't have any of this shared state. It's simple, and we can use C#, which is a big win for a lot of people. C# is a pretty popular language. It's a pretty approachable and productive language too. And we get a low latency and consistency. State is kept in memory. So we don't need to go and talk to other database systems or load data off the disk. We can service requests by the information we keep in RAM. So it's nice and fast. And it's scalable by default and built for the cloud. Really, Orleans summarized in 1 sentence for me is kind of making a distributed system feel like you're programming back in Turbo Pascal with your simple single-threaded application. It makes it nice and simple again. So let's try and keep the slides to a minimum. And I'll do some live coding, and we'll try and knock up a quick Orleans system from scratch. So what I'm going to do is create a slightly contrived Internet of Things demo where we're going to have a device that's going to measure the audio level in the room. It's going to transmit the audio level, the decibel reading over the Azure service bus, which Richard Conway was talking about earlier. And then there's going to be a worker process that's going to read that queue and just take all the messages off the queue. And this worker process will be designed to run across many machines and doesn't have any contextual awareness. It's stateless, so it just naively takes messages off and reads them. So we need a system which will maintain the state of the devices and we'll have grains to represent devices so that we can have a state that remains in memory, and so we can reason about the device and detect peaks in the audio level by looking at the history of the audio level reported by the device. So we're going to build this bit here, which is the Orleans parts, the other bits I prepared earlier. So let's break out of PowerPoint. Make sure you can see my screen. There we go. And we'll open Visual Studio. So I have a project here which has a simple console application which basically just reads that service bus queue here, and every time the message appears on the queue, it handles it and reads the level of the audio in the room, and we'll basically write that out on the screen, and then call this method to, we'll do something later in that. So let's just run that and see that running. That's good, it's doing nothing. Now Microsoft have been building Internet of Things devices for a while now to sample audio levels in the room. They've never really caught on, but they called it the surface. So here it is. So there we go. It should be writing out the audio level there. It should be coming in here. Great, it's not working. That's good, isn't it? Has that got a connection? It says it's limited connectivity to the Shoreditch network. Hey, there we go. So we can see it's writing out the number of messages it's received at the top, the last reading it received, and it should have a little bar of dots that come out showing you the current audio level. So if we go, there we go. Fantastic. So we're ready to roll. So let's go and build the Orleans bits now. So I've installed the Orleans SDK. It's a free download. It's not open source at the moment, but that may change. But you can go onto the Microsoft site and get it. When you've installed Orleans, it adds a couple of new templates in Visual Studio. So you can go into here and select the bits you need. So I think I said earlier that a grain is a C# class. In fact, you need to have a class and an interface. And so we'll create an interface collection first. What should we call it? Any ideas? Stunned silence. Let's try that. So here we define an interface for our grain, which basically says what messages are we going to pass to the grain. So what messages are we going to pass to the grain? We're going to send in the audio level, aren't we? So we'll have everything will be asynchronous, so we will return a task, which is like .NET's version of a promise, and we'll have a set level method. We pass in a double, which is the value of the audio reading. Simple enough? Does it compile? Yes, it does. So that's that done. Now we need to go and implement our grain. So we'll go and create a class collection of grains. What should we call this? Implementation of stunned silence. So here we actually then provide the meat of the grain. So we need to inherit from our interface, or we just defined there. So we need to go and add a reference to that project. Just a stunned silence. And sometimes this works, sometimes this doesn't. No, it's not working for me today. We just pull in that assembly. Will this work now? No. And then we implement the method by saying it's a public, returns a task, it has a set level method, and it has an argument which is a double, which is the value of the reading. So what we'll do is the grain stays in memory while it's being used. So we'll just have a member variable on the grain, which will be a double, to record the last value. And then the first thing we'll do is if the value being passed is greater than, say, I don't know, 35, and the last value was less than or equal to 35, then we've detected a peak in the audio level. It's gone from a quiet level to a loud level, and it's transitioned across my threshold of 35. So we'll write that out to our management reporting system, console.writeLine. It's loud in here. And we must set the last value correctly. Oh, no, it's not. My IntelliSense has died. Does it compile? No. Oh, yeah. It's supposed to be asynchronous, and we've got to return 10 minutes. Great. We've got to return a value. We've got to return a task that's fulfilled to say it's worked and there's no need to wait for this thing. And there's, for our convenience, there's a task done dot done. Otherwise, we could use C#'s async await semantics to provide asynchronous code that doesn't look like a rabbit warren. So that's that grain implemented. So that's the all-ins bits done. When we compiled that, it copied the compiled assembly down to a local silo I have on my machine. So now all we have to do is call the grain and fill out this method here. So we need to get a handle to the grain to be able to send it a message. So in object-oriented programming, objects don't really have an identity because you have a variable that stores that value. But in a distributed system, you can't have a variable that represents your object. You have to have an external kind of identifier. You can use a key to say, this is the object I want to talk to. And so we need a key for our grain. Any ideas for what we could use as a key to identify the grain?
Silence key.
Sorry?
Silence key.
Silence key, yeah. Well, we've got a key already for the device. The device sends over its device ID as part of a message. Probably didn't make that very clear. So we'll use that, and that's a string. Now, by default, Booleans allows you to address a grain using either a double or a GUID. So we've got a string, so we need to go and fix that. So we'll go back to our grain interface and just say extended primary key, like so, and recompile. And what it's done is it's created a factory class for us to get instances of objects which will be a proxy to our grain, if that makes any sense. So we'll get a grain. We have a factory. If I can spell factory. Factory grain what? Grain one factory. Which will just. We need to add a reference to it, don't we? We add a reference to the interface, like so, using stun silence, and we'll get the grain. So now we can pass in two keys, like a primary and a secondary key. Because I went and extended the key, I can just pass in 0 as the primary key, and then the device string as the secondary key. So now we have a grain object here. Now this isn't the real grain, this is just a proxy to the grain. So we call this methods on this object, and they'll be turned into messages which will then be sent to Orleans, where the real grain will be activated, respond to the message, and come back. So we should find what method on this object? Set level. Well, people are awake. And we can pass in the level, like so. And then it's asynchronous. We should await that because it's done a network hop potentially over to another machine where the silo is running, like so. The last thing we need to do is then kind of register or connect to the silo and tell this program where to go to the silo. And that's already set up in an XML configuration file. We just need to say, go and do it. Booleans client dot initialize will do that for us. Super. That's all compiled. Now let's start Orleans up. So we go to let's go to the SDK, and there's a command here to start the local silo. So this is the Orleans silo, but running locally, not in the cloud. And it takes a little while to start up. Spouts out a load of information that I have no idea what it means, but it looks cool. And now we're ready to run our console application. Now that Orleans has started, we now get a whole load of gobbledygook written out to our client application. And when that's ready, I think that's ready, we'll start up the thing again. We're getting readings again, excellent. And if we go back to Orleans, it's loud in here, we've already hit the threshold, but if we, or if you all clap, hey, there we go. It works, it's amazing, so there we go. Normally with these things you have to kind of embrace failure, but it didn't happen today. Is powerful, I'm going to come back. So yeah, so that's the basics of Orleans. 5 minutes left, so I'll just whip through, just name a few advanced concepts, other things you can do with it. So you can have the idea of a stateless worker. So earlier I said that you have kind of one instance of your grain, one activation in the whole of your silo cluster. But in fact you can say, well, I've got a grain that doesn't really have any state, and it's just there as a kind of worker process. You can mark that as a stateless worker. It can be activated multiple times in all of the silos, so it can sit there and process jobs. So when the queue length to it gets to a certain size, it'll spawn new grains to deal with those requests. You can register timers, so if you want grains to run on a regular basis, every few seconds or milliseconds or hours or months, you can set a timer to activate the grain at that point in time. There's an automatic persistence system built into Orleans, so you can call one method to save the state of your grain to a storage system, either a SQL server or a blob or a table or something like that. In fact, you can write your own providers, and it'll go and store the state for you, and then it'll automatically pull the state out for you and apply it to your grain when it's activated. This is a really nice way of storing state. And there's also a pub sub messaging capability built into Orleans, so it can kind of send messages out to listeners. So you could build backplanes to things like SignalR and stuff like that. Cluster membership, so a little bit of the details as to how this thing works. Well, there's different ways you can manage or know what silos are in your cluster. The technique I was using there is I had one silo marked as a primary. In fact, that was the only silo in the system. This is not a particularly good approach because there's no failover if your primary dies. You can lose all your secondaries and the system will continue to work. But with elect a primary silo, it's a manual operation, and you have a single point of failure. So you can delegate out cluster membership to a SQL server, which you can run in high availability if you want to. So you then have no single point of failure, but that's pretty naff. So the best technique is to use the table storage system in Azure, which is what Orleans has been kind of designed to use, which is a high availability storage system built into the Azure platform. And it can store cluster membership information over in that system, and so it doesn't rely on any particular primary silo to be elected in your cluster. Everything is a secondary, and anything can fail. How does it look like in terms of performance? Well, that's a graph. There you go. What this shows you is some of the load testing they did for the Halo system. So this is at least 2 grains cooperating in a response. Very high chance of the grains being on different silos, and it shows you how when you increase the number of servers in the cluster, how the message throughput responds. And what's interesting to see is the graph is fairly linear. I think it will start to tail off more when you add more servers, but it shows you that adding more resource will increase your message throughput, which is a pretty good feature. So, in summary, Orleans makes programming a cluster of machines feel like a single computer. I didn't have to worry too much about the problems of distributed computing when I was implementing my grain, because those problems are taken away for me by the framework. And secondly, it's a great system for building high availability or high throughput or low latency or concurrency. You don't have to hit all of those things, but it can solve any of those problems. It's not the only solution out there. It's not one size fits all. It's not going to run your next blog. It's for a niche of systems, but if you find yourself in that niche, it can really help you. So if you want to know more, if you want to go and download it or find out about it, that's the link to download it, aka ms/Orleans. You just have to fill out a few questions and you get the download. I also set up a contrib project on GitHub where we have loads of extra providers and monitoring systems and all kinds of other stuff. If you're interested in contributing to Orleans or finding more about it, that's a good place to look at as well, or my Twitter.